it's blurry. That's a zoom, I guess. But again, my video should be better. So again, when you have an equipotential, when we talk about equipotentials, you're moving around a surface where V doesn't change. Either E is perpendicular to the equipotentials, or E is 0. And these allow us to map out, believe it or not, electric fields. The electric field lines must always be perpendicular to equipotential surfaces because the electric field is perpendicular to ds. So, since dV is 0, E is perpendicular to ds, and so basically then the equipotentials are perpendicular to the electric field. Okay. All right. Now it turns out that the surface of a conductor is an equipotential. And you might say, well, why is that? So suppose I have a conductor. You get a better marker? Suppose I have a conductor. This is a conductor. And you know that the electric field inside is 0. You also know that the electric field is perpendicular to the surface. Well, if dV is 0 when E is perpendicular to ds, then the surface itself has to be a surface of constant potential. Furthermore, the entire conductor is at a constant potential. Okay. V is a constant for a conductor. Okay, so at the surface of a conductor and inside the conductor, V is a constant. So if I had a, let's say a rectangular conductor, and let's say it's positively charged, and now we're told to draw the equipotential surfaces. Well, the first one would be the rectangle. But then as you get further out, the rectangles, the corners of the rectangle become rounded. They get rounder and rounder. You can say that. And the electric field lines are perpendicular to these. We just got to draw the field line so it's perpendicular to the equipotential. That's it. And many years ago, when we didn't have computers to analyze the electric field due to some sort of configuration of conductors, what physicists would do is they would get a sheet of paper that it's called conducting paper. They would paint, using conducting paint, the conductor onto it, and then with a device called a multimeter, voltmeter, they would measure where the potential was the same value. And we'll talk about the multimeter lab today. So they would go around and measure where the potential had the same value, and they would connect the dots, and they'd see what shape they got. So if it was a rectangle, you'd get something like this. If it was two planes, if you had two long planes, positive, negative, the electric field lines go from positive to negative, and the field is uniform between the planes. Then the equipotentials would just be perpendicular to the field line. So these green lines that I'm drawing are equipotential surfaces. They're equipotential planes. So if I were to do an experiment, I would actually map out these equipotential lines. So I look for everywhere where my meter read 1 volt, and then 2 volts, and then 3 volts. And so I connect all the dots that were at 1 volt. I draw a line. I connect all the dots that are at 2 volts, and that would be this green line. And then I would connect all the dots that were at 3 volts, et cetera, et cetera, et cetera. And then the electric field lines are perpendicular to the equipotentials. That's why it's useful. Okay. So what I want to do now is I want to calculate the electrical potentials due to various types of charge distributions. And this is actually easier to do than the electric field, because there's one thing that you don't have to worry about, and that's determining R hat. This is a scalar. So you have one less thing to worry about. So these tend to be easier to do, especially for the continuous charge distribution. For the discrete charge distribution, this should be for you an easy calculation. And I know some of you have worked ahead of the homework. Let's do a simple example. Let's calculate the electrical potential due to 2-point charges. Electrical potential is a scalar. And so basically, we got to find the electrical potential due to each point charge and add it together. So in this particular example, we want to find the electrical potential at point P. Okay. So let me draw a picture of this system. We'll calculate the electrical potential. Okay. So this charge is plus Q. This charge is minus Q. The distance between them is A. This distance is Y. And here's point P. We know that V for a point charge K, Q, over R. So all I have to do to determine the electrical potential at point P, I got to find the one for the first one at P and then the one for the second one at P. That's it. I'm done. So it's very simple. You guys having a hard time really seeing the Zoom presentation? It could be because my internet's bad. And again, okay, that's strange. So people are having internet issues. That's my guess. It's either on my end or your end. Just remember that the video I put on YouTube will be clear. Okay. Yeah, I try not to give the actual PowerPoint. They're big files, that's why. Okay. Well, let me do this. Let me do this temporarily. Maybe you can see it better. This is the problem I'm working on. Can you all see that better? Okay. The only problem now is you can't see me. Okay. So this is the problem. So I'm going to switch back in a second. So this is the problem we're working on. I did email you the PowerPoint, the class notes. And so this problem is in the class notes. And when I make the class notes, I put blanks on it so you can write notes onto it next to the slide if you print them out. Okay, so I'm going to switch back so you can see me solve the problem. Okay. Maybe I can try this. Maybe I can make this a little bit bigger. So This problem is actually not very difficult because all I got to do is find the potential at point P due to this guy, which is going to be and the potential at this point due to this one. I use it here. So I just need to know this distance. This distance is a squared plus y squared, square root. Okay? That's it, I'm done. I found the electrical potential. That was easy. Okay. And as I said, for discrete charge distributions, finding these are easy. If, for example, I ask you, suppose I put a charge here. All right, suppose I put a charge Q naught, and then let it go in the vicinity of those charges. Okay, let's say I knew which way it went. Okay, because this one's actually harder. But let's say I know which way it's going to go. It goes from here to here. So here's the initial position. Here's the final position. And I want to know what is the change in kinetic energy of this particle. I just use delta U plus delta K equals 0. Delta U is Q naught delta V, where the delta V is the V here minus the V here due to those charges. And then I can use conservation of energy here to solve the problem. Okay. So what I want to do is, I want to calculate the electric field. I want to know E. This is a two-dimensional problem, so I'm going to write it like this. It's the derivative of the electrical potential. Okay, on an exam, most likely the problem is that I do one component. Now, the way this equation is written, I cannot do the calculation because this equation gives me the value at a specific point. I want to see how this thing varies with y, and I want to see how this varies with x. So I'm going to write it in general for any value of x. And then I'll take a derivative. So let me write it as a function of x in general. So I want to find the electric field. Of course, you can find the electric field using the methods that we learned in chapter 23. But it's nice to see it done this way, and then you can compare it. As a homework problem for yourself, what you should do is calculate the electric field based on how you did it in chapter 23 and see if you got the same result. Okay. That's the homework problem for you to practice on. But I mean, it's a practice problem. You have to turn it on. I'm going to take the derivative of this with respect to x, and then it's actually minus the derivative, sorry. Right? It's the gradient. So I'm going to take the derivative of that function with respect to x, assuming y is constant. That shouldn't be hard. You all know how to take a derivative. I should get k, q, x. And this one should be, let's see, negative. Check my math. I took the derivative of this function with respect to x, and then I got to take the negative of it. Oh. New powerful, sorry. Does it look okay? Please check my math. Now I want to take the derivative of that function with respect to y. That'll give me the y component. Well, let me take the derivative of this with respect to y, and then remember, don't forget the minus sign in front. So there's actually three minuses because I take the derivative here. Okay, I have a minus sign here, and then a minus sign from the differentiation. Okay? And it should make sense because the electric field is going to point downward due to this guy. And then I got to take the derivative of the electric field due to this guy. I'm sorry, the derivative of the potential of this term due to the y, which is, I'm sorry, let me rephrase that. The derivative of the electrical potential with respect to y as a result of this charge. So are we okay so far? No, I gotta do one more thing. I don't know if you noticed, I gotta do one more thing. Guess what I gotta do next? Anybody want to guess what I have to do next? I have to substitute the value for x, right? I'm evaluating at the location where x equals a, so now sub. Let me put, or actually minus it, that's going to be squared. And that's it. So that's the answer. Now what you want to do is go back to chapter 23, use the same method to calculate the field. And here's an interesting problem for you to try. I'm not going to do it here. Suppose I have a charge, a positive charge, here. Simple problem. It's a one-dimensional problem. Calculate the electrical potential at the origin. Of course, it's going to be, if this distance is d, we'll call it r. I'm sorry, we'll call it x. Okay? Now, my next question to you is, go ahead and calculate the electric field by taking the derivative. And then think about, does the answer you get make sense? Does the answer you get make sense? Okay? Calculate d, I mean it's obvious, d is kq over x, at point p. Take the derivative of this, right, or the gradient of it, it's only one dimensional, and see if the value you get, the expression you get for the electric field makes sense. That's a fun one for you to try. Right? And you can tell, I mean, the electric field points away from the charge, so the electric field should point in the negative x direction. So see if you get something that points in the negative x direction, you can derivative of this. Oh, yes, you do. So, thank you. And that's got to be an A too, so I should put it like this. No, it's positive, sorry, no. That was my mistake. Because I took the signs into account when I took the signs into account originally. So that should be an A, not negative A, sorry. Because I was taking into account the signs when I derived these equations, that should be an A. So go ahead and think about that one. Okay, so, and if you see anything puzzling, just email me. So now I'm going to do continuous charge distributions. So spend a little bit of time on here. So I want to find the electrical potential due to a continuous charge distribution. It's the same idea as the electric field. When you look at that picture, I have to break up that charge distribution into pieces small enough so that the potential at point P is the same value over that dq. Which means that in general, I have to set up an integral. Okay, that's what it means in general. I have to set up an integral. Point charges are already, they're small enough so that the V is the same over the entire point charge. And so we're going to use a very similar technique as we did for electric field. The only thing is that we don't have to do an R hat. We don't have to figure out an R hat. So our dV is then going to be K dq over R. Again, the only thing missing is the R hat, right? And again, R is the magnitude of the vector that points radially outward from the source to the point. That's always an important thing to remember. So to do the computations, first you have to choose a coordinate system. Then you got to write your expression for dq. You have to determine R. And then integrate. You got one less step. Okay, so this shouldn't be as hard for you because you've already gone through the hardest part. So the more we go through these kind of problems, the easier it should get for you because you get more familiar. I will say that this method is only valid if your charge distribution is finite, because how do you do this for an infinite plane? You can't do it. You can't do it for an infinite plane because if you have an infinite plane, V does not go to 0 at infinity. Using this method assumes V goes to 0 at infinity. Because we're using the K dq over R, that's the expression for the potential due to a point charge, which is defined to be 0 at infinity. So we can't use this for something that's not finite in size, like an infinite plane or a long wire. Okay. So I want to do this example. The setup is quick. Just a second here. So we have a disk instead of a ring. And I want to calculate the electrical potential at point P above the disk. Okay. Let me switch views. And to make it easy, let's assume that the disk is uniformly charged. We have a uniformly charged disk. And guess how I'm going to break the disk up? I'm going to break it up into rings again. And I want to say something about the problem. There's a lot involved, a lot of things you can say about this problem. So let me draw a picture. Best I can. It's 3D. And I'm going to try to use green just because it's lighter. Okay, it's not the greatest disc, sorry. It's already close, but that's our disc. This is point P. It's part of the ring. So the distance here is C, and then this is the radius of my little ring. And now that I have set up the picture, I gotta write an expression for dq and r. R is easy, or big R is easy. I'm going to call it big R just because of too many R's here. The big R is easy because isn't it just the square root of c squared plus little r squared? And isn't dq sigma dA? dA. And this is uniformly charged, so it's going to be a total charge on the disk divided by the area of the disk. And since this is a ring of thickness dr, we've talked about this before, that's going to be our dq. So now our dv is going to be k dq over our big R, and that's going to be k times q over pi a squared 2 pi r squared dr over the square root of q squared plus r squared. So all I got to do is integrate from 0 to a. I got to integrate over all such rings, and that's it. So v, the integral, is 0 to a of this thing. Should the r be squared? No, it shouldn't. You're right. No, r has squared. Thank you. 2 pi r dr. Circumference times dr. Thank you. Okay, so we put it all together into this expression. And I'm not going to talk about the integration technique. That's a calculus problem. This is a problem you can integrate by substitution. So I'll let you think about how to do the integration. It's actually an easy integral, because it's just a substitution. And when you evaluate the integral, you get that expression. So upon integration, you get that expression. So that's the electrical potential due to the disk. So you get 2k cubed over a squared times the square root of z squared plus a squared minus the absolute value of z. That's because of the fact that when you're integrating, you get a z, you take the square root of z squared here. And in fact, if you're really far away, if you're really far away, what happens? If it should look like the potential due to a point charge, right? Well, what if A is really big? If A is pretty big, then you have the electrical potential due to a point. My question then, what I want to ask is, if I know this is my V, if I know this is my V, how do I get the electric field? I actually have to differentiate this with respect to Z. If I want to get the electric field, I want to differentiate with respect to Z, because I know the field's going to depend on the Z direction. Right? The electric field on the axis is only going to be in the Z direction. The components in the plane cancel out, so all I got to do is take the derivative in the Z direction, and that'll give me, well, it's minus the derivative. Okay. But again, if Z, let me go back. If Z is large, I'd have to do an expansion on this term. And you'll see that the only term that survives, at least the first term that survives, is A. Again, A canceling out with an A here, and you'll get 2kq over A for the electrical potential. It'll look like the electrical potential due to a point charge. No father. Okay. All right. Questions on this? Let me look at it real quick another way, okay? Another way to look at it is this way. Suppose I have a ring, just the ring. Just focus on the ring, okay? Isn't it true, if the ring is uniformly charged, I can write the potential due to a ring right away. Why can I do that? Because on a ring, if this is uniformly charged, each piece on the ring is the same distance from point P. And if each piece has the same amount of charge, then each term of my summation has the same denominator and the same numerator. When I add up all the terms, I'm just going to get the numerator over the denominator times the total charge. So having said that, if the next step then is to ask, what is the field due to a disk, then all I got to do is change this to a dq. Because if I want to find the field due to a disk, I consider I'm sorry, not the field. But if I want to find the electrical potential due to a disk, I can think of it as a bunch of rings of thickness dr. So I can start from here right away, and then just say my dq is this expression, and then integrate. That's another way to look at it. Okay. All right. Again, so the last question to ask is, what if sigma is not uniform? Well, if sigma is not uniform, then you cannot pull out the charge distribution out of the integration. Okay. And you have some example problems in the homework. This is a graph of the electric field. I'm sorry. This is a graph of the electrical potential as a function of z. It's symmetric about both sides of the plane, which should make sense because the charge distribution has symmetry about the plane itself. Okay. Notice that the function is continuous at the boundary, which is the plane. The electric potential must be continuous, meaning it must be differentiable. Otherwise, the electric field is infinite, which is not a physical thing. Okay, so one of the important things to learn is that the electrical potential must be continuous across a boundary. Otherwise, you can't take its derivative. The electric field can be discontinuous. In fact, if you calculate the electric field, and I did it in the video, or you can take the derivative of this function, you can get the electric field. The electric field can be discontinuous, and all that means is that you have a charge on the surface. Well, that makes sense because it's a plane, right? It's a plane, so there's a charge that's charged, so that there's a charge on the surface. So the electric field is discontinuous across its surface, but the electric potential must be continuous across the surface or across any boundary. Otherwise, it's not differentiable. Does that make sense? So I want to do one more example. I want to calculate the electric potential due to a rod. We've done something like this. The electric potential due to a rod with a non-uniform charge distribution. We've done a lot of this already, right? We did the electric field due to this guy. And so this shouldn't be that hard. The only thing I don't have to worry about is figuring out what R hat is, because I'm calculating a scalar. So let me draw a picture for this. Here's the x-axis. Here's the rod. Here's an element of the rod, Q. The element is a distance x from the origin. This guy is, the length of the rod is L. The distance to point P from the end of the rod is A. And again, this is the x-axis. So the distance from this element of charge to point P is going to be this distance minus x. So I already know what my R is. So I already know my R. Okay. Now I got to figure out my dq. This is linear, 1d, lambda dx, and this is going to be lambda naught x dx. And look, we did this problem before, so I don't want to spend time re-deriving what lambda naught is. You've done it in one of the homework problems. So I will say what lambda naught is. It's 2q over L squared. And if you don't remember, you should actually go back when we calculated electric field for this problem. or you should go back to problem number 9 on the first homework set. Okay? It's fun. These kind of things you got to remember pretty much for the whole semester. And you've done things like this in Physics 205, previous course. But it's not something you need, something you want to always remember. Okay, that's it. So my dV is going to be K times this thing. And then L plus A minus X. And all I got to do is integrate that. And then, yeah, it's fun. It's fun to discuss the integral. But this ain't a calculus class, so don't tell your calculus teacher I'm skipping this. But I'm going to, in the interest of time. And so when you integrate this over the entire length of the rod, you will get the following expression. And if I want to calculate the electric field at point A, at point P, to find E at point P, you got to take the derivative of this with respect to x. So that means you have to substitute the value of x in here. Well, maybe rewrite this, say replace a with x. Then take minus the derivative with respect to x, and then sub back in a. And what you'll do is you'll get this. Which is what we had before, right, with I hat. That's what we did in chapter 23. Okay, so look, we have a lot of practice you can do with these problems. Go through this, evaluate this, and then take a derivative to get the electric field. And then the other questions, I asked it when I did the problem in chapter 23, if you're really far away from that line charge, then you should get the electric field due to a point charge, and you should get the electric potential due to a point charge. Those are questions you can ask yourself. Okay? Now you can see the setup in these problems is a little bit easier. But again, in all these problems we've done, the electric field problems, the B problems, you have to know your dq, you have to figure out your R. Okay, and then for the electric field, you need your R hat. I now want to show you another way to calculate the electric potential. And this is the way that works in every single case. What I had done in the previous two problems, I used the idea that the electric potential due to a point charge is K dq over R. Because I assumed V was 0 to infinity. Okay, and that equation, K dq over R, basically came from the expression you see up on the screen now. which is this one. Okay, that KDQR really came from this. This works in every case. And so this will allow me to figure out the electric potential or the electric potential difference due to some charge distribution that's not finite in extent, something very long, like a long wire, or a long cylinder, or a plane, where I can choose a different point for V, where V equals 0. So all I got to do is integrate the electric field over some path. It ain't gonna make a difference what path I choose because this integral is independent of the path. So I pick a path that's convenient for me. Of course, you have to know the electric field, right, to the charge distribution in order for you to use this. Okay. You have to use this when the charge distribution is not finite in extent. That's important to remember. Okay, the two problems I just did, you cannot do for a plane. Let me rephrase that. The two problems I did, the technique that I used, cannot be used for a plane. Okay. So it is more general than just the integral k dq over r. And it's related to the work done on a charge by a field and moving it from point A to point B. And the last homework problem on the assignment is basically a problem on this. The last homework, or second to last, I forget. Last or second to last problem in the homework is based on this idea. It's very important that you understand that V is defined up to a constant. So different people can define their V to be 0 at different locations. Really what's important delta is the delta V, not the actual value of V, because the delta V represents that work is being done. V is just a value. So whether you define V to be 0 at infinity or x equals 0, doesn't matter. But the value of delta V is what's important. I want to use this technique to calculate the electrical potential due to a uniformly charged insulating sphere of radius r. This is a solid sphere. And I can choose whatever path I want. You have a solid sphere, uniformly charged. And to save time, let me write down what the electric field is inside the sphere and outside the sphere. Okay? So let me draw my sphere, and then I'll just write down the expression inside and outside. E inside right, in fact, this equation listed in the book, and the test I want you to be able to derive that equation. Okay, I'm doing this, I'm just writing it down just to save time. Then E outside. There's no charge on the surface, right? So it's continuous. So I want to use my expression. I want to write V. I actually want the actual value of V. Now, in order for me to be able to use this, I need to know the electric potential at some point. Otherwise, I'm screwed. Okay? I need, in order for me to find V as a function of position, I need to know the electric potential at some point. Well, this is a sphere. This charge distribution is finite in size. Okay? So I'm going to say, oh, since sphere is finite, then I'm going to say V equals 0 at R equals infinity. And I'm always going to integrate outward. My unit vector always points outward, and my limits of integration will be used to really define whether I'm going outward or inward. The R vector, the vector that represents the electric field, is always, it's always going to be positive. It's these two that's going to tell me the direction I integrate in. So really, I know the electric field, I know the electric potential is going to be 0 at R equals infinity. So I know that. And so what I'm going to do is I'm going to say V final minus V initial is equal to minus the integral from infinity to some point in space R of the electric field on these primes here. My E dot ds, my E is in the R hat direction. And in fact, it looks like this. I should be unit vectors. The only component, I'm just going to integrate in the R hat direction. It doesn't matter how I integrate. Okay. R hat points outward, and I'm going to integrate outward. I'm going to make my path this way, even though my limits are going to be backwards. It works. So what does this give me when I integrate this? It's going to give me minus k over R from infinity to R. Which is plus, sorry. When I integrate, I got another sign. And so this is going to give me K, Q, over R. And so V final minus the initial. The initial is the value of infinity. This goes to 0. But everywhere outside the sphere, that's what the electric potential is. What about inside? What about inside the sphere? If I want to find the field inside the sphere, I got to start at the surface and integrate inward. I know what the potential is going to be at the surface. At the surface, V is K, Q, over the radius of the surface. And so my V initial is going to be the value of the potential at the surface. So I'm going to do V final minus V initial minus the integral of the electric field This time I'm integrating this guy because I'm inside the sphere. Again, I'm integrating radially. And I'm going to call these primes again. Now when I integrate this, what am I going to get? Okay, so let me continue over here. Remember, we initialed the potential on the surface, so I'm going to put that value in. Let me put in my limits. And then this is going to give me that. Let me double check my algebra. Yes, I think we're fine. Okay. If I can rewrite it in the following way. I think I made a sign error. We got the minus sign. Okay. So when I rewrite this, I'll get the following. I just rewrote it. So what's the name of the game? You start at a point where you need to know where the field, the electric potential is known or defined. And then you integrate inward. Usually you start outward and integrate inward. Okay? Which is what I did. This is typically what you do. You start outward and integrate inward. You need to know the value of the potential at a point in order for you to be able to find V as a function of position. Now notice that if you plot the electric field, we've done this before. Let me use a different color. We plotted the electric field for a sphere, and it looked like this inside the sphere, and it went over. It was dependent on 1 over r squared outside the sphere. And the potential is the integral of this, so it's minus the integral of this, basically. So electric potential is going to be 1 power higher if you integrate something that's linear. And so that's going to give you a parabola, but it's going to be upside down because of the minus sign. And this is going to be 1 over r function. And in fact, this is what the electric potential looks like when you plot it. And the electric potential has to be continuous across the surface. Okay. So let me blow this up. So V naught is basically, we can define V naught as the potential at the center of the sphere. On the surface, it's 2/3 of that value, and then it goes down. So we can define the value of the electric potential at r equals 0 to be V naught. You can call it whatever you want, right? And then at 2/3 that value, at the value of r, it's 2/3 that value. And then outside the sphere, it decreases. It's 1 over r. Okay. Now, suppose you have two long concentric shells. And you want to calculate the electrical potential between the two shells. They're both uniformly charged. They're both infinitely long. You actually had a similar problem like this in the homework, except you're finding the field. I want to know the electrical potential for this system. Okay? I want to know the electrical potential for this system as a function of R. By the way, what's going to be the electric field outside of the two shells? What do you think? What's the electric field going to be outside? Yeah, you're right, it's 0. Because if you apply Gauss's law, how much charge is enclosed? 0. And so the electrical potential outside of the two conductors is going to be a constant because the electric field is 0. And that constant is going to be defined by what is V on the outer surface. And typically, to set this up, what you do is you get a battery and you connect the terminals of the battery to either one of the to both conductors. So if the other one is at 3 volts, then everything outside of the cylinders is at 3 volts, the whole region of space. Okay. If you connect the ground to the outside one, then everything outside is 0 volts. Okay, so let's do this. And I'm going to just write down the field due to a line of charge. I don't want to use Gauss's law and derive everything again in the interest of time. We've done that before, anyway. So let me draw this again. This is actually an important problem in the next chapter when we talk about capacitance. When you talk about wires and you're measuring small signals, you can have wires that store energy on that can affect the signal. So it's kind of an important problem. So the inside one's minus lambda, the outside one's plus lambda. We know that E out equals 0, and E in, and where E in is between these two spheres is going to be, and I'm just going to write it down, okay? It's 2k lambda over R. This is the Coulomb constant. And it's radially inward, actually, because of the minus sign. The field actually points inward. Okay. So I'm going to use this expression to evaluate the electric potential in here. Because I don't care about here. I know it's a constant. The constant will depend on whatever the potential is on the surface. Because there's no field outside. Who cares? In fact, there's no field in here either, inside a conductor. There's no field inside the inner shell, and then there's no field outside, it's just in between. So I'm only interested in between. So the potential in here is going to be whatever the potential is on the inner conductor. The field out here is going to be whatever the potential is on the outer conductor. Remember, the potential has to be continuous over boundaries. It has to be, because otherwise the electric field is not defined. And let's go back to your calculus and what kind of function is differentiable. Okay, so I'm going to do this integral, and what I'm going to do is I want to find the potential at some arbitrary point R. Okay, from the center. And so I'm going to set up the integral it's man like that. Well, I can move. Okay. And I'll be done once I'm done with this problem. Sorry. Okay. And I'm going to integrate from here to here. I know what the potential is there. I'm going to define the potential there. Okay. Let me make sure that. Okay. So let's say I want to integrate from R to A, which is the integral. Then the final minus the initial is going to be the integral of R to A 2k lambda over R dr. And this is going to be logarithmic. And when I evaluate this integral, I'm going to get, let me check my signs, I don't want to silly here. For 1 second. Yeah, we're fine. And then the final one here is A, so I can call this B sub A. It really doesn't matter. I mean, why am I integrating from R to A? I know the potential at A, right? I define the potential at A to be B sub A. If I want to find the potential between the two, if I want to find delta V between A and B, which I'll do next, okay, then I integrate from A to B or B to A. Doesn't matter, right? It shouldn't really make a difference. If I want to find the delta V between A and B, I can do VB minus VA. If I switch it around, these two switch around instead of these two, so it doesn't matter. Does that make sense, Martin? Right, I mean, if I switch these two, then these two will switch together. All right, if I integrate from B to A, oops, that's wrong. Right, here's my initial, here's my final, here's my final, here's my initial. If I flip these two around, then I flip these two around. the sign, I change the sign on both sides, right? I get the same result. I just want to make sure that's clear. Whether I go from here to here, or from here to here, or from here to here, that's going to flip both terms around. So I'm basically multiplying both sides by -1 on the equation. And that cancels. Okay. So if I do this, then this is going to give me b sub a minus b sub b is equal to natural log. Keep it in there. Sorry, I'm trying to hurry up. 2k lambda natural log of a over b. Or I can write it b sub b minus b sub a as minus 2a lambda natural log of a. It doesn't matter, right? They're both the same. In fact, I can write this in more ways because I can flip this over and get rid of minus sign. Are we okay with that? Okay. I went over. I wanted to cover this. I need to cover something else in the lab, so just to make sure we cover everything. Whatever I'm covering in the lab is going to be not as complex as what we're doing here. And I wanted to do that here. Okay. So in the lab, I'm going to talk about a couple of applications. A couple of our basic and one's a little bit more involved, and then I'll be done with the chapter. I still want to say a couple of things about applications. And if what I did wasn't clear here, please don't hesitate to email me. All right, so I'm going to stop here, and I will talk about applications of this idea in the lab, and then I'll talk about the new lab. And we have several weeks for the lab, so we have time to talk about the material in the lab, okay? All right, we'll see you in about 12 minutes, some of you.